Well, good morning, afternoon, everybody. I'm George Fadel calling you from the United States. So welcome to Design for Additive Manufacturing 3, D432. We have 5 papers, and papers address different aspects of additive manufacturing. We have a paper on functional integration, a paper on cost, a paper on part preparation for repair, a paper on the potential of additive manufacturing use, and a paper on conformity. So 5 aspects that are very important for the field of additive manufacturing, and hopefully we will see how these things build upon each other and basically help us moving forward. We will go through the presentations one after the other, so all 5 presentations will be presented, and then we will have the question and answer session. So please do enter questions on the chat area so that we can look at them later on and discuss them. So with this, Philip, if you could get started with the presentation, I appreciate it. Thank you.
Hello and welcome to my presentation. My name is Steffan. I'm a research associate at Darmstadt University of Technology. And today I present the results of my research on the methodical consideration of function integration through hybrid integrating additive manufacturing technologies in the following referred to as high AM. In this paper, characteristics are derived from existing high AM product examples which are used to optimize a mechanical arm prosthesis. High AM are hybrid technology combinations that integrate additional components due to the flexible layer-by-layer process of additive manufacturing technology. It is possible to integrate additional components into the part during production. In this hybrid part, electrical and mechanical components described in the literature, such as nuts, batteries, and resistors, are embedded in the body during the printing process. At the Institute of Product Development and Machine Elements, a high AM is currently being developed using the fused filament fabrication process. The process can integrate electrical and mechanical conductors, for example Bowden cables, in a geometrically flexible way. A possible integrated part is shown in the picture on the left-hand side. The potentials of the functional integration of these processes open up new design freedom for the development of products. But high AM manufacturing is not appropriate for every part of the product. We want to know which components are beneficial for the use of high AM specific potentials. In order to find these beneficial components, functional characteristics are derived, which are used in the product development process. These identify characteristic functional areas in the function structure and their corresponding components for which additional partial solutions made possible by the high AM to consider them in the development process. This procedure was successfully tested for additive manufacturing within the framework of the extended approach. The result is the consideration of the potentials of hybrid integrating additive manufacturing during the early concept phase in the product development process. In order to derive characteristics specific to high AM, documented application examples were collected from the literature. From these examples, the function structures were formed. Subsequently, the areas that were made possible by the integrated components were analyzed. This revealed 5 characteristic configurations of the function structure that occur specific to the high AM. First, the interface-motivated integration for the simplification or elimination of interfaces between components. Second, the manufacturing-motivated integration of the simplified assembly of components during component production. Third, the functional-motivated integration for the functional expansion or optimization. The fourth characteristic is integration of auxiliary functions for minimal influence on the design. And the fifth, integration of auxiliary functions for isolation of function carriers. The first 3 refer to the function structure immediately during or after its creation. The characteristics 4 and 5 are usable after the specification of the functional carriers. For a first evaluation of the high AM characteristics, they are used for the further development of a mechanical arm prosthesis. The arm prosthesis consists of a body for the upper arm and forearm, which are connected by a joint. The prosthetic hand is mounted at the lower end of the arm. To open the hand, the muscle power of the wearer is transferred to the hand via a Bowden cable. Due to the very short time available, the function structures themselves will not be discussed in detail in the following. To use the high AM potentials, the function structure is formed and analyzed with the new characteristics. In particular, the function transmit tractive force, which appears twice, was found to be suitable for integration into the upper arm and forearm. Both functions are fulfilled by adjacent components. Furthermore, they are necessary auxiliary functions to enable the movement of the forearm and hand. These auxiliary functions interact with the environment and can get caught in obstacles. This can be prevented by shielding environmental disturbances. This corresponds to the presented characteristic 3, 4, and 5. These incentives are used to vary the function structure. The transmit tractive force functions are integrated into arm segments made by a high AM, which form an integrated functional area. For the design of the prosthesis, the function carriers of the corresponding functions are relocated to the inside of the upper arm and the forearm in form of Bowden cables using high AM's technology. In the final design, the Bowden cables are integrated into the forearm and upper arm during additive manufacturing of these two parts with high AM for integrating mechanical conductors. The achieved advantages are a reduced component entanglement, less components, and reduced assembly effort. Summing up, we use the function structure to reduce the complexity of the product model. 5 characteristics are derived to use the high AM potentials from examples in literature. The characteristics found were used for the further development of a mechanical arm prosthesis. So what's next? The following questions arise. How can we link the AM design possibilities of function integration and the integration of components? How will the approach behave in a large development project? And how can the high AM technology be used for a further customization of the prosthesis for user-specific lengths and shapes? These exciting questions bring me to the end of my talk, and I look forward to a lively discussion. Thank you very much.
Thank you. And we'll have the second presentation. Please enter questions.
Dear participants, this is Mikhailo Sartini, a PhD student from Università Politecnica delle Marche in Italy, and now I'm going to present you the paper entitled Cost Sensitivity Analysis for Laser Power Bed Fusion. LPBF is an additive manufacturing process that uses a heat source, the laser in this case, to scan and to melt layer by layer material powered together. An increasing number of companies are using this new technology to manufacture their product. Knowing how to manage the cost means having a more competitive product. So from one hand, design engineers must quantify and evaluate the cost of their design solutions through a properly developed cost model. On the other hand, design teams should be aware of additive manufacturing cost drivers to develop a competitive product. And sensitivity analysis allows designers to identify such cost drivers. Different studies can be found in literature regarding cost estimation of additive manufacturing technology and in detail laser power bed fusions. Unfortunately, the cost models available just provide equations without any process parameters. The present work attempts to improve the existing cost model by developing an analytical cost model with further details than ones available. Then, after its validation, the proposed cost model is used to perform a cost sensitivity analysis. Here, we want to give a quick overview of the main cost items of the proposed cost model. The calculation model was conceived considering the following cost items: material cost, machine cost, labor cost, consumables cost, and energy cost. And the cost models aims to predict the cost regarding the pre-process and build process phase. To evaluate the material cost, the approach established in this study considers powder recycling. We provided a commercial value to the recycled powder obtained from the printing job that can be reused. So the main parameters involved are the volume of virgin powder filled on the printing chamber, the volume of reusable powder, the percentage of powder lost during cleaning and filtering operations, the cost per kilogram of virgin powder, and the cost per kilogram of reusable powder. The last has a lower price due to consideration about the powder's degradations. The machine cost consists of three cost items: setup, idle, and operation. Setup time refers to the time needed to fill the chamber with powder, load the plate, and manage the CAD file. The idle time includes plate heating time, cool down time, and plate and powder removal time. The operation, so the build time, is the sum of recoating and scanning times. The first depends by the maximum height of the component in the printing direction, the layer thickness, and the time that recoater takes to distribute a layer of powder. The scanning time is the time spent by the laser to aggregate the powder and build the solid model. It depends on the hatch distance, the number of layers, layer thickness, component volume, and perimeter passes. Of course, it also depends by the scanning speed of the laser, given by the linear energy density and the laser power. The cost is then obtained multiplying this time with the hourly machine rate. It depends on the hourly rate of deprection, maintenance, and production overhead. This hourly rate further depends on more precise data, the load factor above all. The labor cost is the cost while the operator prepares the 3D printer, while he unloads the build platform, and while he attends the printing process. The consumables consider the costs related to compressed air and gas consumption to inert the chamber. Energy cost represents the machine's energy consumption during the warm-up, building, and cool-down phase. Before introducing the sensitivity analysis, a cost model validation has been done. To do this, we have considered 8 components proposed by a manufacturing company that produced this part internally. For a correct comparison, the same information and parameter values used by the company were included in the model. So same printing direction, same batch quantity, material cost, machine hourly rate, and scanning parameters like layer thickness, edge distance, and overlap rate. The results are great, so the model can be used for the sensitivity analysis. Moving to the sensitivity analysis, the variables considered for the study are grouped into 2 types: product parameters and process parameters. For the first one, volume and print height of the part have been considered. For the process, 7 variables were considered: load factor, layer thickness, print speed, recoating time, raw material cost, energy cost, and labor cost. The analysis was performed changing those variables from the starting condition until they reach values equal to -80% and +80%, with steps of 20%. For each parameter, 9 observation values are determined. Furthermore, the cost model updates automatically the dependent process parameters when changing the observed variable. Considering our 8 components and 5 different materials, we obtain a database with 360 cost values considered for each observed parameter. Analyzing the trends result for the product parameters, titanium has the highest cost sensitivity concerning the part height, with a value approximately double that of aluminum. Concerning the volume, aluminum has the most significant sensitivity. This result is also due by the process parameters used for both materials. Considering the process parameters, load factor, print speed, and layer thickness, they show a hyperbolic sensitivity, while parameters like raw material price, recoating time, energy price, and labor price, they show a linear sensitivity. From a global point of view, regarding the product parameters, the part height has a higher sensitivity than the volume. Among the process parameters, the load factor has the most significant impact on the printing cost, followed by the layer thickness. Moving to the conclusions, it is possible to say that the analytical cost model used for the sensitivity analysis is useful to identify the most relevant product and process cost drivers. From the obtained result, the load factor, the layer thickness, and the raw material price are the 3 most cost-impacting process parameters for the laser-powered bed fusions. Future work will improve the cost model with an integration of post-process phases and related sensitivity analysis. Thanks for watching, and for further details, here are my contacts.
Hello, my name is Nicola Viktoria Ganter. I'm a PhD student at the Institute of Product Development at the Leibniz University of Hanover. I would like to present you a knowledge-based assistance system for additive repair by laser powder bed fusion. Motivation. In the industrialized nations, we are faced with the challenge of having to reduce our resource consumption. One strategy is to extend the service life of damaged components. Metallic components can be repaired and upgraded by additive manufacturing processes, which is called additive repair. One of the additive repair processes is laser powder bed fusion. The process is based on the principle that a recoater applies a powder layer to a building platform like a squeegee. Then a laser selectively melts the powder material. For a repair, the component must usually be prepared in a milling process. A flat plane must be produced on which the powder material can be applied by the recoater. After the additive process, functional surfaces are post-processed. In order to select an appropriate plane for the laser powder bed fusion process, expert knowledge is necessary. The position and orientation of the plane influences the technical feasibility of the repair, as well as the resource input, the process duration, and the quality of the repaired component. The difficulty in determining the section plane is that a large number of aspects influences the suitability of a plane, sometimes even contradictory to each other. Moreover, many criteria are difficult to evaluate visually or manually. Therefore, our goal is to support the determination of the section plane by providing the necessary expert knowledge. For the selection of a suitable section plane, it is necessary to analyze the geometry and the volume of the damaged part. Therefore, our approach is to develop a knowledge-based engineering system which is integrated in a CAD system. Such a system allows to analyze a CAD model and to draw conclusions based on it. This is done either by analyzing the geometry and abstracting it into parameters, or by evaluating the structure tree of the model, which represents the design history. In order to build the system, we first collected the essential requirements for the choice of the section plane. The criteria are: first, the entire damaged volume should be removed through the section plane. Second, part areas that are to be intentionally changed in the repair process, for example, for a functional upgrade, have to be removed by the section plane. Third, the minimum amount of undamaged material should be removed. In particular, it should be avoided that undamaged functional surfaces are cut off. Additionally, the plane should be chosen so that the necessary support structures in the LPBF process are minimal. Compared to an additive manufacturing process, support structures bring the additional disadvantage in additive repair that a special fixture is often required to provide a platform on which support structures can be built on. Based on these criteria, possible section planes are analyzed in the system. We built the system in the CAD program Autodesk Inventor using the VBA programming environment. Input for the system is the CAD data of the undamaged component. In the CAD model, the user defines the damage and areas to be modified by extruding a box. By naming the extrusion uniquely as error or refurbishment, it can be identified by the program in the structure tree. In addition, the user selects which evaluation criteria should be prioritized. For example, that priority is given to removing as little undamaged volume as possible. Furthermore, the user selects how complicated the part design is. This input controls how many potential section planes are generated and analyzed by the system. Finally, one selects which data should be output. Then the system is started. Within the system, a large number of section planes is automatically created. The planes are generated in such a way that the error extrusion and the refurbishment extrusion are completely cut off. This slide illustrates 6 of the generated planes. In the following, the generated planes are analyzed with regard to the evaluation criteria. For this purpose, the model is separated at each plane and the volume of the cut-off part is read out. Then the system analyzes whether a plane intersects functional surfaces such as holes. Holes are identified in the system through their designation in the structure tree. To determine the necessary support structures, the angle of body surfaces to the section plane is retrieved. For this purpose, the model must first be saved in an STL format, since surfaces are tessellated there. A limit value for the angle is stored in the system, above which support structures are required. After the analysis, only the plane with the best evaluation remains in the CAD model. The other planes are deleted. The model is separated at this plane. Through the separation, two solids are created. The solid representing the undamaged part area is saved as a model. It is the documentation for the part preparation. The model representing the part area to be rebuilt is also stored separately. It can be output as STL for the LPBF process. To conclude, an assistance system was presented which supports the selection of a section plane. The section plane is required for the repair of a component in the laser powder bed fusion process. The presented knowledge-based engineering system analyzes the geometry of a part through the CAD model and its structure tree. In order to test the reliability of the developed expert system, it was applied to different components. The system generates successfully a section plane for all considered use cases, which ensures that the damaged part area is completely removed. However, the application of the system also demonstrated limitations. The system does not recommend the most suitable section plane with respect to the evaluation criteria under certain circumstances. In the future, we want to address these limitations and further improve the system.
Hello, my name is Pascal Schmidt, and I would like to tell you something about our paper, Rethinking System Boundaries for Better Utilization of Additive Manufacturing Potentials, a case study. The paper shows an approach to optimize a triathlon bike for the use of additive manufacturing. The redesign was carried out as part of a student project. And fun fact, you can see this student on a triathlon bike here. Triathlon bikes have a quite complex shape, and they are already in lightweight design. We focused on the front area, which is called aero bar and supports the driver in getting in an aerodynamic position. Separated, this system can look, for example, like this on the bottom right, like this, or like this, depending on the anatomy of the rider. A closer look at the system shows or helps to detect some unused potentials. For example, aero bars usually doesn't fit closely to the rider's arm due to the different geometries, which causes turbulences. And rides on the aero bar can last sometimes for hours, which can lead to pressure points. It has few integrated functions to keep the complexity level low, and the high number of fasteners shows the fact that the lightweight potential isn't exploited. The approach is based on a previous work that has shown the need to adopt the architecture of the product to meet lightweight potentials by using AM. So the use of a functional modeling approach was thus predefined for the project. For the detection of the practical system boundaries, the student decided for a one-part device by Ernstspiel, which starts with maximum theoretical system boundary. I will focus in this presentation on the last 2 points, the changing constraints by determining design space and changing the design space, because these were worked on with the function modeling approach. The student chose a method called enhanced function means modeling instead of other methods of function modeling, for example, the IFM. He argued this decision with existing preliminary work in which the EFM was explicitly proposed for application in the field of AM. In this method, dependencies of design solutions and manufacturing constraints are described. Thus, design spaces can be detected quickly by changing manufacturing processes. Related to this method is also one of the research questions of this paper. Can the advantages of integrated modeling of function and system architecture be used for conceptual lightweight design with additive manufacturing? The enhanced function means model, the application of this model, can be subdivided into the following steps. First, to define product architecture. Second, create an enhanced function means model for an existing product. Create an adjusted model that's simplified by removing or deleting constraints and associated design solutions and functional requirements that are caused by originally manufacturing limitations. This serves as a transitional model to redesign and makes the design space visible. And the last step is to fill up the design space with new AM-related solutions. Taking a closer look to this model shows on the right top the main function, and the new model is still based on the same main function, but the sub-functions are adapted slightly. New design solution variants are integrated now into this model, and I will give a short example because of the limited time here. The hand position according to the anatomy is solved by extension and direction of travel, and this requires the function of handle position according to the anatomy. This is solved by a long curved body, and this requires again the function of reduced weight. And then there are different solutions related to AM. For example, topology optimization, thin walls with lattice structure, carbon part, where AM is used for tooling. So this model set a base for an assessment where a promising approach was considered further. And this one is based on a parameterized and topology optimized model with a carbon shell. You can see this result here. And in addition to the main goal of saving weight with 32% map reduction compared to conventional bars, this also includes improved ergonomics and a potential improvement in aerodynamics. You can see the result here as well. For a conclusion, I would like to say that function modeling here by DFM can be beneficial for detecting the design space. It helps comparing different impacts of different design solutions. But for redesign at this level of abstraction, detailed knowledge about the structure of the system is necessary. And as you could see, it tends to become confusing at some point. So scalability can be important for larger systems. This opens up the question of which types of redesign the method is advantageous and to what extent existing function model methods explicitly for additive manufacturing need to be adapted. Thank you for your attention.
Hi, I'm Gregory Jamie Tizin from the University of Stuttgart. I'll be presenting to you our paper about additive manufacturing conformity, looked at from a practical perspective. This study aims at describing key aspects to consider while conceptualizing and designing additively manufactured parts. In the next few minutes, I'll be explaining to you the need, the methodology, and the results of our research. But now let's focus on a single question. What even is an additive manufacturing conformal design? In the last couple of years, a number of methods have emerged to support the design process, focusing additive manufacturing and improve a function-oriented design. And with that, function-related design restrictions emerge that are formulated within additive manufacturing conformity. Allow me to outline the situation. When we think about functions, for example, channeling some sort of energy from place A to place B, we are searching for a solution principle. We then find a fitting solution principle, which implements a given function through a combination of physical effect plus a specific geometry and material composition. Without consideration of manufacturing processes and functional constraints, we may create a non-functional part design. A better way or a better step would be to consider AM conformity early on and design our solution principle with regards to function-related restrictions. That way we reduce potential design iterations later on. But what does it take to integrate those restrictions into our design? We use criteria to formulate these restrictions, but existing literature either focuses a theoretical or solely practical perspective. Within our study, we address the gap in criteria between a theoretical perspective and a practitioner's perspective to establish a holistic set of criteria for AM conformity. And it is this research gap that leads us to the following question. First off, how big is the gap in criteria sets that assess AM conformity between both perspectives? And secondly, what aspects from a practitioner's perspective can be added to our existing criteria? In search for an answer, we consolidated different literature-based criteria, applied them in several use cases, and validated the practicality. One of these use cases was illustrated in our paper. And instead of describing every criterion, we want to present you the need for functional optimization as an exemplary one. Let's take our previous example. When integrating the hinge, our solution principle, directly into a final part, it breaks across the flexible structure. By adding parallel structures, the excessive degrees of freedom have been restricted, and thus the function fulfillment has been optimized. We added these types of examples plus a short description with more detailed elaboration on how to check your design for several criteria. After considering all criteria, we achieved a AM conformal design. We followed up with a study focusing on industrial participants who were experienced and knowledgeable about additive manufacturing. 96% of our participants utilize additive manufacturing technologies for both prototypes and final parts. Some even consult throughout a development process specifically for additive manufacturing. Then measure the level of agreement for each criterion for each participant. And with all that data, a statistical evaluation was necessary to examine the collected data for significance and to draw conclusions about their relevance on individual criteria. The level of agreement of 28 participants was measured using liquid type data. For our example, functional optimization, the evaluation returned a median of 4.32 on a 5-point Likert scale, resulting in general agreement with this criterion. Assuming a referential median of 4 for each literature-based criterion, a sign test indicates that there is a positive discrepancy between literature and practice, simply because the median is greater than the reference. Furthermore, the significance P of our result is equal to 0.3, which in return is statistically meaningful. So we conclude that in this case, the criterion for assessing AM conformity, so functional optimization, is of great significance to practitioners. But now we only know how relevant our aspects on AM conformity are from a practical point of view. To establish a holistic set of criteria, practitioners were asked about missing aspects when it comes to part design. And after a thematic analysis, 5 new aspects were identified, of which the left side was added directly to the existing criteria, while the consideration of sustainability was deemed as a separate criterion. Based on these few additions, we conclude that the existing literature-based set of criteria covers almost all aspects of the practical view apart from sustainable design. From our point of view, a designer needs to reflect on manufacturing constraints and function fulfillment early on. And criteria assist in assessing AM conformity and therefore considering function-related restrictions in theory and in practice. Furthermore, sustainable design should be taken into account, which requires appropriate design guidelines and further research. After a literature review, use cases, and an empirical study, what's next? The form in which the criteria should be provided remains unclear, perhaps as heuristics with self-explanatory examples or in the form of a checklist. After all, the goal is to develop a repository of AM-conformal solution principles to combine an opportunistic approach in finding specific solutions while addressing the constraints imposed by AM conformity early on. With this summary, I hope I've provided you with more insight into our topic. I look forward to your feedback.
Thank you, everybody, for your presentations. Very interesting talks, and we appreciated that you all recorded your presentation, which allowed us to go very quickly through the presentation. So we're going to have about 39 minutes. So we've got plenty of time to discuss the different presentations. And what I'll do is first, I urge you to put more questions, and we'll go to the top and start going through the questions one by one on each topic. So the first paper was on function integration through design of our hybrid integrated additive manufacturing technology. So the presenter was K. Eric, Werner, Heinz, Steffan, but we have Michel Fett, Michel Fett, who's going to answer the questions here that we have. And so I had a question here, and we'll see what the others are. So Michel, are the approaches you use for high-AM depend on the additive manufacturing process you use? So would you have a different approach for the different additive manufacturing processes that are available?
Well, thank you for the question. At the moment, we don't make a difference between the different processes. The reason here is that in the literature, there are many different additive manufacturing processes combined with many different integration processes. And there are many interdependencies, and at the current stage, we are not able to take these into account, but these are point of further research.
Okay. Yeah, it'll be interesting to think about it. How do you integrate? How do you do it for basically maybe for each process you'll have a different approach?
Yes.
So we have another question from Pascal Schmidt. How exactly, this is to Michel again, how exactly are the components integrated during the printing process? Do you stop the printing and put the parts, or do you have some kind of a mechanism or a robot, or how do you do it?
We do not print the components. This is not multi-material print. And again, the most of the higher M approaches or processes we found in the literature, they're not exclusive from us. And they are different again. Some of them interrupt the printing process. They leave small holes in the body and interrupt the process, and then, for example, glue the components in the holes, and then go on with the printing process. On the other hand, there are higher M processes which have a special kind of printing head. This is mainly on FDM processes. They have a special printing head which can integrate cables, for example, or continuous elements. So here the printing process is not interrupted. It is more in a parallel matter.
Yeah, I mean, there are issues of if you're using a laser-based thing and you're trying to embed something that is maybe affected by the high energy or high heat, how do you do it? So there are some interesting challenges.
Yes.
One question, and if anybody else has questions, please do put them in the chat so that we can capture them and then go over them. I had a question about that actually to many of you. I think we have a majority of German papers in here, 4 out of 5 and 1 Italian. And you use, all of you use function-based approaches or some variations of function-based approaches. And I've always struggled with function-based approaches as being taught. For me, a function is a transformation. So you have an input, you transform it to an output. And many times when you look at functional approaches, the way they have been described in Paul and Bites and others, they're not necessarily just a transformation. And so how do we deal with some of these issues when they are not transformations? Is the functional-based approach sufficient, or do we need something else? I don't know. This is an open question if anybody wants to address it. Otherwise, we can move on. I'll give you a second to see if anybody wants to tackle this, but we have a question from Gregory that maybe addresses some of that. He said, instead of looking at your function structure, would it be beneficial to tackle function integration through a design structure matrix?
We decided to go on the function level because it's a quite abstract view on the product, and we thought that you have the biggest leverage when you want to change something, and that's the main reason because of the leverage.
Okay. All right, let's move on to the next paper by Mikhailo. And I'm going to start with Jose's question. It says, very interesting. Could you please explain in which phase of the product development do you recommend to apply cost calculation? Do you need to fix the AM details, part geometry, materials, process? It would be good to get the cost info already in the would it be good to have the cost at the conceptual phase?
Okay, well, thank you for the question. First of all, I don't know if it was just my connection problem, but the recording had some lag and was not very understandable. But I hope that you can hear. Well, for the question, okay. For a few parameters are required, so the cost model can also be used in concept design. Obviously, having more detailed information like geometry, like materials, allow a more accurate estimate to be obtained.
So you think it should be done at the conceptual phase?
Yes.
Okay. Jose, is your question answered? Well, I had questions. I felt that you have addressed most of the issues that you would need in a cost model. And my question was, I mean, you do take into account how much you're using new material, how much you're using recycled material and things like this. And so you can get the cost. But then by changing these proportions, you may have different performance responses. So how do you address this issue of I mean, if I know how much I'm going to use, yes, I know how much it's going to cost, but how do I know what should I use in terms of mixture, for instance?
The choice of material depends on performance, and it is therefore a design driver to be given as input to the cost model. The value of a recycled powder found in the literature does not take into account peculiar aspects that can occur in high performance parts to be made in qualified process. So our cost model, the aims of our cost model is only to give only to quantify the cost of a design solution, not taking into account the behavior of our components in terms of mechanical behavior, mechanical aspects.
Yeah, but you could tie your cost model with an optimization where you have a trade-off between performance and cost, because you have a way to calculate it based on some parameters, and you could modify these parameters and see basically what would be the best approach, possibly.
When an engineer estimates the cost of his component, he has no idea how much recycling the powder may have done or how much it is degraded. He only knows how much powder has been used, how much has been melted down, and how much has been recovered. So one of our parameters is giving a commercial value to the used powder obtained from the printing job. And this allows the engineer to have the cost of the material used and at the same time consider the possible degradation of the powder. So there is a difference between the cost of virgin powder filling in the chamber and an economic value of the recovered powder. And the economic value of the recovered powder is 70% of the virgin powder cost, and this value was obtained through market research on the marketing of recycled powder and with the support of a company that tested our cost model. So it's just a balance between these two different powder, the virgin powder and the recovered powder, reusable powder.
All right, thank you. Okay, let's move on to the paper by Nicola on really looking at repair using laser powder bed fusion approaches. So let me see which question I'll pick first. Pascal had a question: do the criteria for the quality of printed components with the LPBF process for additive repair differ from rapid manufacturing in general?
Thank you. I think for the quality, there's only one difference, and this is that you always have a certain offset between the repair volume and the old part. So you need to consider that this offset should not be in an area where the offset is bad regarding the function of the part, and in an area where you can't post-process it. That might be in an area where you have internal channels that you can't post-process or inner structures. I think that's the only quality or the only evaluation criteria regarding the quality. The others that differ between AM and additive repair are more regarding the cost and the duration of the repair process. For example, that by the decision on the section plane, the volume that you need to apply in the repair process differs, and therefore the duration and cost.
Okay. The question by Philip is a very interesting one. So you basically look at coming up with your cutting plane to figure out where to remove material and to repair. But then how do you support the structure to build it so that you can put that material back on? So what is the trade-off between the ease of holding the part and where you're going to decide to cut your part?
Yeah, sorry, I need to.
So if we read the question, he says, you need to use fixtures to add support structures. So you need to think about holding the part, but you also have to think about the heat that you have in the part.
Yeah.
And how do you decide on the cutting plane based on these additional criteria?
Yeah, that's a very good question. So in our practical repair studies or use cases, the section plane was always decided by aligning the functional surfaces, vertical or horizontal, to the building platform, and the building platform is always parallel to the section plane, because otherwise it's really, really hard to mount it on the building platform. When we rotate the part regarding the building platform, we only did it by around one axle, because otherwise it's just too hard to align it manually. Regarding the heat, up to now we just did use cases in steel, in MS Heinz, and we only the parameter to heat up MS Heinz is only 40 degrees. So therefore the heat transfer is not such a big topic there. But I think it would be probably more problematic if we would do repair cases in aluminium or in other materials where you need to heat up more. Probably there you need a machine that heats up the surface of the powder bed instead of the building platform. But we didn't look at this too much yet because we did not had the problems with the steel parts.
Okay, thank you. There's a question by Yuri. He wonders if the repair approach is more convenient or effective, if your approach is more convenient or effective than using directed energy deposition, which would allow you to not worry about planes, basically place material wherever you want. Have you considered this aspect?
Definitely. It's really hard to find use cases for repair by LPBF. The majority of additive repair is always done by direct energy deposition, and it will be in the future, pretty sure. But there are certain parts where direct energy deposition is not suitable for repair. For example, if you need to restore a structure where you have filigree structures, internal gas channels, then LPBF is more convenient or more applicable repair technology. So it's a niche.
Yeah. Definitely an interesting question to think about it. But also, I mean, it's a broadening of the use of additive manufacturing. So I had a question on, do you use optimization to decide on the best solution for the section plane? And you've kind of answered this question saying you're looking at basically putting it in the bed. But I wonder if there is a way to maybe hold the part, should you try to use optimization to figure out what is the best plane that material and still addresses you need?
It would make so in the I think for the section plane decision you have a variety of evaluation criteria, and in our system we implemented 4. It would definitely make sense to implement optimization algorithm, but we didn't yet. So yeah, it would make definitely sense. Up to now, we're like in this prototype, the user defines which one is the evaluation criteria that is most important. And then for this evaluation criteria, the system searches for example, for the minimum volume, which is cut off by the section plane. But especially if for a user, a trade-off between different evaluation criteria is important, you need an optimization algorithm.
Okay, thank you. And I think there's one more question from Gregory. How sensitive is your assistance system in terms of its effectiveness? I don't know, Gregory, if you want to add to that.
Yeah, I can elaborate a little bit, because my question more so addresses if you have an automation or your assistant system, it's not always the case that your results are always the same, depending on the criteria you checked on before. That's what I call, or what I call effectiveness. If your results are always the same, what I wanted to know is how much are your results differing from each other with more iterations you do on your simulation.
So we in the system there are no iterations implemented, because we generate. It's very easy solved right now. So we just generate a certain number of planes that is fixed depending on the complexity of like you have 3 possible steps, how many planes are generated in how many angles, if it's a 5-degree step angle, 3-degree or 1 degree. And those are analyzed regarding 4 criteria. And then up to now in this prototype, the criterion that the user gave priority to, this therefore it is looked which one is the best plane. Therefore, there are not several iterations.
All right. Yeah, I get it. Thank you.
All right, thank you. So let's go to Pascal. So basically looking at rethinking system boundary for better utilization of additive manufacturing potential, and a case study of design of the handlebar of bicycle, a race bicycle, I guess. So it was interesting again for me to look at this approach based on functional decomposition, trying to figure out how to come up with the solution. But I was trying to understand, how do you address the trade-off in requirements between strength, comfort, aerodynamics? You do an analysis. I mean, I'm sure you did an analysis to think about strength, but what about issues of comfort, issues of aerodynamics? How do you address that?
Yeah, thank you for your question. So the material property were taken from a fiber reinforced plastic, which was printed by FDM, and this is called PDX, and were used for the topology optimization. And the load cases were taken from a standard ISO standard. And to the evaluation, I would like to say that, of course, we need the weight that is can be measured well. There are some aspects that aren't easy to measure. The ergonomic, for example, is more like an rather an objective feature. But as you can see, maybe the contact surface is now significantly larger, which can be seen as one point of an increased ergonomic. And but a validation of for example, the aerodynamics is not carried out so far. So it's an improvement in aerodynamics. Sorry. So far, only is assumed. And yes, of course, in addition, the product was manufactured using FDM, and the influence of the manufacturing behavior and, for example, anisotropy wasn't taken into account, and this may lead to that the safety factor has actually to be increased, which would lead to increased weight again. So it can be seen as a prototype, I think. Mm-hmm. But and even it looks maybe right now, especially without the shell, it looks more voluminous compared to the traditional Erebus system. Important is the effective cross section, which can be seen from this side, and yeah, there can be assumed an improved aerodynamic, but yeah, it's not proven so far. So,
well, I think you partially answered the next question, which is, did you use a systematic approach to modify your selected solution variation? So, from what I understand, you use topology optimization, right?
Yes, topology optimization. But I understood the question as well as could in order to the selecting of the solution. I don't know, Gregory.
Yeah, I can elaborate that. It went both ways. One thing would be answered with the topology optimization. The other thing is, well, it's a little bit abstract. You have your creative process, right? And you select your individual solutions or solution variants. But it's also interesting, simply phrased, how did you come up with your variations?
Yeah, good question. The approach, the EFM, is, yeah, it doesn't serve or brings the ideas, so it needs to be complemented with creativity approaches, for example, creativity techniques. Yeah, this is only, it can be seen like the morphology matrix. So it's a space where you can put the ideas or the solutions, but it doesn't brings up the ideas or the design solutions.
So basically, you know where to look at, but it's still a creative process, and you use creativity techniques to find your new solution variant, right?
Yeah. It was the framework where to put the ideas and the solutions, and to analyze the interactions of the new solutions with the already or the still existing design. But it didn't help to bring up these solutions.
Okay,
it's just a framework.
Thank you.
Okay, thank you. Please remember to add questions if you need to. And if not, I guess we'll go to Gregory's paper. And first, I was impressed by some of the statistics you put, 96% use of additive manufacturing and things like that. That was really very impressive. So my question was, what processes are mostly used? I would assume it would be different whether you're using it for a functional component or a critical component, or for just an aesthetic aspect and things like that. But can you address what are typically the processes that are currently used?
Sure. Well, it's a bit of a tricky question, because what I would need is a correlation matrix comparing your process and if you used a functional part or if you want to use a prototype. Because both ways, well, 96% use additive manufacturing technologies for prototyping, and also 96% use it for functional parts. It is quite easy to come up with an answer. Most people used fused deposition modeling, or your fused filament fabrication, whatever you would call it, disregarding if it's a prototype or a functional part, what I found quite interesting. But also a lot of people are using laser sintering and laser melting. Couple of participants said that they would utilize different resin techniques, but most have a portfolio of selective laser melting, laser sintering, and fused deposition modeling, and switch in between, depending on if it's for specific material they design, or if it's simply for example, spare part or anything like that.
Yeah, definitely. So my other question was, you talked about sustainability, and I was trying to think, how would you consider sustainability? Material use, energy use, recyclable material, things like this. I think Yuri is here too, and he may be interested in that, since he's looking at the cross between sustainability and additive manufacturing. So any ideas?
That's also quite tricky, because I'm remembering the workshop where Yuri was also in, with the presentations of David Rosen and Jeremy Faludi. They also suggested a couple of strategies, and that's where I have probably my biggest challenge right now, is how can I have, for example, design guidelines for sustainability addressing additive manufacturing early on, because I'm looking at solution principles. And now you had a couple of suggestions, for example, material use or material usage. We could address that with a strategy of, for example, structural optimization or function integration. Same goes with the recyclability of our material, depending on which material we are choosing or what material requirements we are focusing on beforehand. Probably will be obsolete, or even a factoring point in our design. Difficulty comes up with the energy use, or let's say energy consumption. And actually, I don't have, for now, I don't have an idea how I will translate the energy consumption where you use a whole part or have a full-on product to simply concepts. Actually, that's probably the difficult part on it. But a lot of strategies, or a lot of factors we have in the sustainability part can be challenged, can be answered with the existing criteria we already have. For example, functional optimization I already have presented in my preview.
Yeah. Okay, anybody else has a specific question to any of the authors? I think I've looked at most of the ones that have been posted. Anybody? No additional questions? We have a few more minutes, so let me take a couple minutes to first, I don't know how many of you are members of the Design Society Special Interest Group on additive manufacturing, design for additive manufacturing. I'd be curious. Nobody? So you may want to consider this. I mean, if you join the Design Society, I think it's like £20 for PhD students to join, and you have a ton of papers that are available, but you do not necessarily have to join the Design Society to be able to be a member of the Design for Additive Manufacturing. But there is a lot of papers and things that are published at the Design Society website, which may be helpful for you guys to look at. So I would strongly encourage you to consider this. Gregory, I think you asked at the beginning in terms of what did I see? I mean, I can tell you that when we started working on additive manufacturing, the main issues were, okay, how do we represent it as accurately as possible in CAD, and what kind of formats are available and things like that. And then what processes are available and how do the processes affect the parts. So it's interesting to see that a lot of these aspects are now considered solved, and what we're seeing is that there is a lot more complexity in additive manufacturing because we have the ability to do things that we've never been able to do before. But there is a significant needs to be able to better come up with analysis tools. I mean, when we're using additive manufacturing, whether, for instance, the Pascal's handlebar, so you're using a composite, you're using a resin and fibers, and you have certain properties that you're using, but are these properties really correct when you're applying them using an additive manufacturing process? So how do we ensure that this is correct? Do we have standards that are evolving in terms of what do we use? And we all know that there's more and more parts that are used in airplanes and cars and things. So the parts, the technology has become at a certain point where it is acceptable and it is used for functional aspects too. But there's always this aspect of validation and how do we make sure that the parts are doing what they do. What I see the future is really more the complexity, the embedding parts into others, the ability to do. Actually, I have a part here that I always put on the side that I can show you. This is a part that was designed using topology optimization. It is in titanium, but it has the properties of hard rubber. So it has a nonlinear behavior based on the geometry that is designed in here. So to start really opening up the design domain and try to think, okay, what can I do with this process that I could never do before, for me is a fascinating area. All the use of in the biofield, I mean, printing organs, making skins, making whatever it is. I mean, just think about where the technology will take us in the next years. It'll be really fascinating. And you guys are the ones taking it forward. I'm all behind you. So any questions from anybody? I guess I'll thank you all for your presentations and for your questions, and wish you the best. And maybe we'll see you in this next gather location. So take care and have a good day.
Thanks again.
Thank you.
Thank you.
Thank you. Bye.
Thank you very much.
Bye.
Thank you.